Hello everyone, welcome to the Gather Knowledge with Mihai channel. This video is part of the series covering some interesting C++ projects that I have developed on my free time. Since I'm an engineer with a major in automotive engineering working in the programming area, I always like to combine as much the two fields. This is why in this video, we'll be exploring the fascinating world of Bézier curves and how to implement them in C++. Our end result will look something like this. We can manipulate the points in any way we want to create a complex curve. This is called a quadratic Bézier curve, and this will be the topic of this video. As such, the main goal of this video is to offer a comprehensive understanding of Bézier curves in C++ and equip you with the necessary skills and knowledge to incorporate them into your own projects. It doesn't matter if you are an experienced or beginner programmer, you will only need simple notions of mathematics and C++ programming. Throughout the video, we will first cover the fundamentals of Bézier curves, what they are and why they are useful. We will go over the underlying mathematics and give a small introduction to graphics library in C++, SDL2. In the end, we will code together a small graphic program to demonstrate the usage of Bézier curves using the aforementioned SDL2 library. By the end of this video, you should be able to, first of all, understand the fundamentals of Bézier curves and the mathematics behind them, be able to implement a simple graphics project using SDL2 library, and implement Bézier functions in C++ to generate smooth curves and shapes. So, if you are ready to dive into the world of Bézier curves and explore their capabilities in C++, let's get started. Bézier curves, as they are called after the French mathematician Pierre Bézier, are mathematical functions that are used to create and manipulate complex curves. They are constructed using so-called anchor points and control points. Bézier functions provide a way to interpolate between the control points, enabling us to define complex curves and paths with precise control. Bézier curves are at the heart of numerous applications in computer graphics to create smooth and visually appealing shapes, paths, and animations. They offer a powerful and intuitive way to manipulate graphical elements. Whether you are interested in game development, graphic design, or 3D modeling tools, understanding Bézier functions is a valuable skill to have. By understanding how they work and how to implement them in C++, you'll gain the ability to create visually stunning graphics and animations with fine-grained control. Let's jump into the mathematics of the Bézier functions. Every Bézier curve has two anchor points, which are the extremities of the line. The control points are used to obtain the complex shapes. A quadratic Bézier curve involves one control point, and a cubic Bézier curve has two control points. Now, before we go into the actual mathematics, we need to define what is an affine combination. An affine combination or transformation is a linear combination where the sum of the coefficients is equal to 1. So, a linear Bézier function has only two anchor points and no control points. It is simply a series of points obtained by doing the affine combination between the 2 points, or put simply, a straight line between the 2 points. So the Bézier function is defined similar to this. P0 plus t multiplied by p1 minus p0, or written differently, 1 minus t multiplied by p0 plus t multiplied by p1 with t between 0 and 1. As you can see, it is an affine transformation as 1 minus t plus t is equal to 1. But how do we use this equation? As we are in the 2 dimension, each point has an x and a y coordinates. So, we get an equation for both x and y coordinates for the points on the Bézier curve, which represent, again, the linear transformation for the respective x and y coordinates. For example, for the x coordinates of the Bézier curve, we get x coordinate of the p0 plus t multiplied by the x coordinate of p1 minus x coordinate of p0, or again written differently, 1 minus t multiplied by the x coordinate of p0 plus t multiplied by the x coordinate of p1 with t again between 0 and 1. The same goes for the y coordinate. A quadratic Bézier function has two anchor points and one control point. It is an affine combination of two linear Bézier functions, one from the first anchor point to the control point, and the other one from the control point to the anchor point. So it's 1 minus t multiplied by the first Bézier function from p0 to p1, plus t multiplied by the second linear Bézier function from p1 to p2. As t increases from 0 to 1, the curve departs from p0 in the direction of p1, then bends to arrive at p2 from the direction of p1. Now, this one, written differently, it results in p1 plus 1 minus t squared multiplied by p0 minus p1 plus t squared multiplied by p2 minus p1. Again, this can be replaced with x and y coordinates to get the actual x and y coordinates of the points on the Bézier curve. The cubic Bézier function can be defined again as an affine transformation of two quadratic Bézier functions. So it's 1 minus t multiplied by the first quadratic Bézier function plus t multiplied by the second quadratic Bézier function. In this case, p0 and p3 are the anchor points, and p1 and p2 will be the control points. So, written in the final form, it would be 1 minus t to the power 3 multiplied by p0 plus 3 multiplied by 1 minus t squared multiplied by t multiplied by p1 plus 3 multiplied by 1 minus t multiplied by t squared multiplied by p2 plus t to the power of 3 multiplied by p3. Again, here to get the x and y coordinates of the cubic Bézier functions, we will replace p0, p1, p2 and p3 with the respective x and y coordinates. Now let's do a small introduction to the SDL2 library of C++. We will try to do a small dot in the center of the app screen. Normally, I use SFML library. For this project, I use SDL2 library for graphics. First, we set the build system via Conan and CMake. In my Conan file.txt, I specify the SDL library with the version that I want to use. In this case, 226.1. Then, in the CMake file, in the CMake lists.txt, first we look for the SDL2 library. We add the executable to be created, include the directories for the headers, and finally link with the library. I also set some properties to use C++20. We won't be using any C++20 features in this video, but I like to have the possibility to use the latest features. In my C++ program, we first include the SDL header and the standard headers that we will need. We also have to specify #define SDL main handled because we have a main function in our application already defined. Without this, the linker, when we link against the SDL2 library, will find two main functions defined and will throw an error. Then we define the screen width and height. Within the main function, we first call SDL init to initialize the library, and this takes as argument the SAS system to initialize, for example, SDL init video or, also a possibility, SDL init audio. Then we create an SDL window object to display graphics and handle user input events. SDL window shown flag is to make the window visible. And finally, we also create an SDL renderer object responsible for the actual rendering of graphics onto the window previously created. The SDL create renderer function takes as input the window pointer on which you want to perform the rendering. The -1 represents the index of the rendering driver to use. By passing -1, we let the SDL library choose the first available renderer. The last argument is the flags that define the behavior of the renderer. SDL renderer accelerated indicates that hardware acceleration should be used for rendering. Finally, on exiting the main function, we have to make sure to clean up all of these objects. I have another video on how to do this nicer with modern C++ features, smart pointers in this case. We will have a big loop that will be exited only on certain events. First of all, even before the loop, we initialize some parameters. Then, in the loop, we clear everything that is already in the renderer. Not useful now, but will be needed once the things on the screen change between iterations, like moving objects. If we don't clear the renderer, we'll print both the old and the new positions of those objects. We set the background color to black, and once we are done drawing, we can call SDL render present by passing the renderer pointer to render everything to screen. We then see if we have any events waiting in the queue, and we react on them. In this case, I only handle the quit events so that it is easy to exit from the screen. I also added a small slip at the end so that the loop doesn't spin continuously. Finally, we need the actual function that draws the points. For that, we will use the SDL color struct from the SDL library. We pass in the renderer pointer, the XY coordinates of the center point, and the radius. We also pass in the color that we want for the point to have. We will need to differentiate later between anchor points and control points. We go through all the points that belong in the interval xy minus radius, xy plus radius, and we see if that point belongs to the circle. If it does, we color the pixel. The function will be called within the main loop. Now let's test and see if this actually works. So everything seems to be fine. We get a blue point right in the middle of the screen. For Bézier functions, we will mostly need to compute the affine transformation, aka the linear interpolations. For this, most programming languages have a specific function. C++ has one as well, std_lerp. It is similar to these functions, but much safer and more versatile. First, we will define a point struct. We will also create a new lerp function accepting 2 point structs as arguments that returns a new point which will represent the linear interpolation value between the t points at value t. This function will call std_lerp for both x and y coordinates. Then, we will define a new function for calculating quadratic Bézier functions. And we will need to define another function for calculating cubic Bézier functions. Now, let's go to the main program. We create 3 vectors of row pointers. We are using row pointers because they will not own the points. Small parentheses. In C++, it is totally fine to use row pointers if you respect the rules suggested by the C++ committee, the core guidelines for using them. In this case, the vectors will not own the points, they will just use them so they don't have to care about memory management of the allocated resources. Then, we create the actual control and anchor points, add them to their specific vectors, and merge them to a common vector for better control over all points. We also need a bunch of extra parameters. Point radius is the radius on the circle center within which all pixels will be colored. dt is the increment used for the linear interpolations. Drag point is related to what I mentioned earlier. The point is saved while being dragged to be easier to change its positions. Bézier curve is the series of points that form the actual Bézier curve, and we reserve an estimated initial size so that the vector doesn't have to reallocate a lot. The boolean running is used to be able to stop the outer loop when exit commands are issued. The main loop will look like this. First we set the render, we then draw all anchor points in green and all control points in blue. We then calculate all points on the Bézier curve, add them to the vector, and draw each one of them in red. Now let's have a look at the SDL event loop to process events. As in the small SDL tutorial we have quit on pressing the X icon of the application and on pressing the escape key. We are only interested if a key is pressed if it is the escape key. This is why I did not use a switch statement but a simple if. If we press the mouse button, the SDL mouse button down event is issued. We want to identify if the mouse clicks on one of the points, control or anchor. This is why I created a big vector with all. We iterate through all the points and we calculate the distance from where the mouse is to the center of the point. If the distance is smaller than the radius, then it means that we clicked on a point and we want to drag it. In this case, we save it within the drag point pointer. Once we unclick the mouse button, we release the drag point pointer. We will not be dragging that point anymore. If the mouse is moving and the drag point exists, it means that the mouse has been clicked on a point and we are currently dragging it. As such, we simply change the drag point's position to the new mouse position. I implemented the whole dragging logic to be able to see how complex curves can be created using control and anchor points. Excellent, we now have our own graphics program to play around with Bézier curves. Let's see if it works. Everything is fine, we can move the control points, we can also move the anchor points, and we see how the Bézier curve goes. We can play more with it. We can reduce the dt even more to increase the number of shown points. So if I put here 005, I start the program, I see that I can move, I get even more points. And we can reduce it even more to get a smoother line. Now the line is actually quite smooth. I can play with the points all around and I can create any shape I want. Thank you for watching to the end and I hope you learned something new. Please let me know in the comments what other interesting projects I can build using C++, what you liked in this video, or how it can be improved. If you like what you saw, don't forget to like and subscribe, as I'll try to post videos about interesting topics as often as possible. Thank you very much and see you in the next video.